A company called AppHarvest built what was supposed to be the future of farming in the middle of Kentucky. 200 acres under glass, hydroponic systems, robots handling the harvest. It went public at $1 billion valuation, backed by Martha Stewart and J.D. Vance. And then it collapsed. Not because the technology failed, the vegetables were perfect, but because the electricity bill made the whole thing uneconomical. And that failure, I think, is the key to understanding why the countries with the worst soil on Earth might end up controlling the world's food supply. We're going to trace why vertical farming really failed, what small nuclear reactors change about that equation, and why the nations that currently import almost everything they eat could end up growing it themselves. If you've been following this channel, you've seen this pattern before. We looked at how the retirement system was designed for a world that no longer exists, and this is the same kind of structural mismatch. An architecture built on assumptions about energy that are about to shift. Chapter 1. Why did vertical farming fail? A few years ago, vertical farming was going to change everything. Towering skyscrapers of lettuce grown in the middle of cities. No soil, no pesticides, no weather risk. Billions of dollars poured into companies promising to revolutionize how we grow food. AppHarvest was one of the biggest names in that space. They built a massive facility in Kentucky, went public, had celebrity investors. The pitch was compelling. Appalachia could become a year-round food production hub, and the technology did work. They were growing high-quality produce in a controlled environment. But here's what the hype missed. Running a vertical farm takes an enormous amount of energy. All those LED lights, the climate control systems, the water circulation, it adds up fast. When you're plugged into a standard electricity grid, energy alone can eat up something like a third to a half of your operating costs. If electricity prices go up, and they always do, the numbers just don't work. So AppHarvest filed for bankruptcy, and a lot of people drew a simple conclusion. Vertical farming was a Silicon Valley fantasy that couldn't compete with dirt and sunlight. But here's the thing about that conclusion. It assumes the energy price is fixed. It assumes these farms have to plug into the same grid as everyone else, pay the same rates, deal with the same fluctuations. That assumption is the weak link, and once you pull on it, the whole story looks different. Chapter 2. What changes when you remove the energy constraint? There's a technology that's been slowly making its way through regulatory approval that most people are talking about for the wrong reasons. Small modular nuclear reactors. The debate about them is stuck on whether they're cheaper than solar for the grid. I think that's missing the point entirely. A small modular reactor, roughly the size of a backyard shed, puts out about 50 megawatts. That's enough for 40,000 homes. Or it's enough to run a vertical farming operation that produces something like 9,000 tons of leafy greens a year, regardless of what the weather is doing outside. Now think about what that changes. The fatal flaw in vertical farming wasn't the concept. It was the energy source. When you're tied to a grid that runs on natural gas and solar, your costs will always be unpredictable. Gas prices spike, solar drops at night, and the farm needs power 24 hours a day. But what if the farm doesn't tie to the grid at all? What if it sits next to a dedicated nuclear module that delivers constant predictable power at a fixed cost for decades? The energy cost becomes something you plan around, not something that can break you. The uncertainty that killed the vertical farming industry is simply removed. This is the angle that the entire SMR debate is missing. Everyone's arguing about cost per kilowatt hour, comparing it to solar and wind for grid electricity. But the real question is, what can you do with dedicated, dense, reliable power that you couldn't do before? And the answer is, you can grow food anywhere. Chapter 3. Who wins when food can be grown anywhere? Let me give you a concrete example. The United Arab Emirates imports about 85% of its food. They sit on desert, some of the worst soil on the planet. One disruption to global shipping or trade routes, and they're looking at empty shelves. They have nuclear power. The Baraka plant generates over 5 gigawatts, but they don't currently use it for food production. Now think about the incentive structure for a moment. A nation that depends on food imports is strategically vulnerable. That vulnerability has real geopolitical consequences. Countries like Ukraine and the United States have leverage because they grow the grain. Brazil has leverage because they grow the soy. The nations that import those staples pay a premium, not just in money, but in political dependence. Now imagine you're a country with bad soil and good energy. You deploy a few small reactors in desert areas, build climate-independent food production facilities, and suddenly you're growing a significant portion of your own fresh produce. The soil doesn't matter. The climate doesn't matter. What matters is having enough energy density to run the lights and the pumps. In Australia, we've seen this dynamic play out with water. The states that controlled the Murray-Darling Basin had leverage over the states that didn't. Water rights were a source of political power. The same principle applies to energy. Whoever controls dense, reliable, decentralized energy will control the capacity to produce food independent of geography. The countries that benefit most from this transition aren't the ones with the best farmland. They're the ones with the most deployable energy per square kilometer of barren land. Chapter 4. What comes next? There's a precedent for this that doesn't get mentioned in the food conversation. The Haber-Bosch process, invented over 100 years ago, takes nitrogen from the air and turns it into fertilizer using massive amounts of energy. Today, it consumes roughly 1 to 2% of all the energy used on the planet. We are already spending that much energy just to manufacture one input for agriculture. The step from manufacturing fertilizer to manufacturing the food itself is not as big as it seems. So the question isn't whether controlled environment agriculture can work. It already works. The question is which energy source makes the economics work at scale. And that's where the conversation needs to shift. The current debate about small modular reactors is stuck on whether they can compete with solar. That's the wrong question entirely. The right question is, what happens to global food logistics when you remove the energy constraint from production entirely? The answer changes the geopolitical balance. Nations that currently have no agricultural leverage because they have bad soil or bad climate suddenly acquire a new kind of leverage. And nations that currently rely on their breadbasket status start to lose some of that advantage. This shift won't happen overnight. The Haber-Bosch process took decades to scale. Small modular reactors are still in early deployment, but the direction of the incentives is clear. Energy density is becoming the most important variable in global food security. And the nations that understand that, the ones that stop asking whether SMRs are cheaper than solar and start asking what energy enables, are the ones that will control the next chapter of the story. If there's a system you want me to pull apart next, a technology, a market, an industry where the conventional wisdom is missing the real mechanism, drop it in the comments. Because the assumptions that everyone shares are usually the ones worth questioning.